Hello, my name is Dermot Doran, and I run a research unit in the area of safety and dependability in the Institute of Embedded Systems at the ZHAW based in Winterthur. One area of current research is the area of safe and dependable neural networks, and I want to present some results out of this research domain. Specifically, I want to talk about application of redundant architectures applied on machine learning or AI systems. The motivation is that we see an increasing use of embedded AI on the edge in industry today. And we also see the desire for ensuring dependability heading towards the area of functional safety. And we want to provide a contribution to this area, and we do so in this presentation by examining redundant architectures which are well understood and well applied in industry to try and achieve this dependability. So first of all, I want to talk about what forms of dependability we're actually trying to achieve. And then I want to talk about architectures. How can we achieve this in the AI domain, embedded AI domain. And then I'm going to present the results of some experiments that we have done specifically on GPU and FPGA platforms before presenting our conclusions and suggesting further work. If we try and build dependable embedded systems, we need to verify in three domains. First of all, the model. Does it do what it's supposed to do, and can it be made dependable? Can it be made functionally safe? And how will it achieve that functional safety and the safety functions that go behind it? Then we have to verify the implementation of the model. That is the process by which we implement this model, circuit design, code verification, etc. And then while this implementation is actually in the field and running, we have to make sure that the integrity of execution is guaranteed according to the specified limits. Well understood process, often used in industry with support from chip manufacturers and software tooling. In a neural network application, there are considerably more steps in the workflow required to achieve a runnable model. We have to design a model as such, which is expressed both in the neural network architecture and in the input data that we intend to train it with. We know, for instance, that neural networks are very vulnerable to input data manipulation. We also know that the designer will tend to specify a neural network architecture, a number of neurons, layers, connectivity between those layers, and that the designer will also tend to reflect his internal biases in the choice of input data. So the integrity of the model as such is questionable. Then we have the area of the learning environment. Does it actually do what the designer intends? And what we see here are iterative processes where the designer attempts to achieve, say we're in classification, a 90%, 97%, 98% recognition of the test data that he or she presents to the taught neural network. Again, we have the issue of bias here. Then there's also the implementation workflow. That is, I have a neural network, it's been trained on a substantial machine, and I have to convert this to something that's going to run on an embedded runtime platform. Current trends in research in AI, we hear terms such as explainable AI, auditable AI, responsible AI, and these are terms that express the lack of understanding of the generation of a model and the teaching of that model. Very early stages in the workflow of creating a neural network or AI system. And there's substantial funding and research in this area. And what we see are industry practitioners that are willing to deal with some uncertainties in their AI applications, but what they also want to see is a convergence on dependable and eventually functionally safe systems. So we're providing a contribution in this area, and our first step is to investigate well understood techniques to try and guarantee that the AI is functioning correctly. We're not looking at the models, but we're looking at the implementation layer. And in this area, redundancy is a well understood technique, has been well applied in industry and well understood by industry, and typical for dependable systems. Neural networks are a computationally expensive implementation, and we need platforms that can handle this computational expense within temporal limits. And GPUs and FPGAs tend to be the platforms of choice in this area. So if we look at redundancy architectures, we have 1 out of 2, which is 2 system series. If one fails, the circuit will break. We can guarantee a certain dependability of operation here. If we have 2 out of 2, we have 2 systems in parallel, one can fail, used to extend availability, and 2 out of 3, if 2 fail, then the circuit will break. We can use this to ensure both dependability and extend availability, if of course we ensure the maintenance of that platform. This system or this architecture is also extendable to M out of N processing units in our case. So we're looking here at 1 out of 2 systems in this presentation. So how do we achieve this in practice? Well, we're talking about embedded systems, which is generally speaking embedded processing. And we have tightly coupled lockstepping, very well understood in industry, very well supported by integrated circuit manufacturing companies. And we have 2 processors. They are synchronously clocked. They operate on the same data and code. And we look to see what these processors are doing on a bus level, that is agnostic of the code they're carrying out or the data they're actually manipulating. And if the 2 processors differ, then we assume that some error has occurred, and we generally assert an interrupt or a reset, which will cause the computing platform to restart. There's also loosely coupled lockstepping. The operations are carried out redundantly and potentially asynchronously. So it's not a synchronous operation, and in this technique we compare the results of operations, that is the data that each of these operations generate, and if we have a problem there, then we perform some sort of error recovery. So what do we require to realize a redundant architecture in these techniques using the components that we have seen before, which are basically the GPU and FPGA architectures? And in this body of work, we are looking at a naive approach. We are taking all off-the-shelf units and applying these things without any optimization to see how these things can function in a redundant system. Neural networks, again, computationally expensive. We use multiply and accumulate operations. and we have complex parallel circuits to perform these operations. The architectures benefit from a vectorization of operations over multiple functional units, and tightly coupled lockstepping of these dedicated architectures is often impractical and expensive, also difficult to achieve. So we see that loosely coupled lockstepping is much more practical for complex circuits. It also facilitates diversity in hardware and software, so we reduce the probability of systematic errors. We allow greater flexibility in the applications, also in what happens if an error in operation has been detected, but it introduces a degree of asynchronicity which we have to compensate for. That is, if we want to compare output data, the output data has to be available for a voter or a checker at the same time. So we want to look at this potential asynchronicity and see what we actually have to deal with. So if we take a GPU application and we try to make it redundant, then we have a GPU, which is in itself a complex system. It is generally speaking used in an environment where we have a feeder CPU that feeds the GPU with both data and executable code. And this will make for a complex redundant circuit, as the CPU-GPU tuple will require its own memory and own input ports and signal conditioning circuits. So we have subsystems which are essentially independent of each other in such a redundant architecture. We also have the issue here that the GPU is essentially just a processing machine. The instructions and the data are given to the GPU, and this is the feeder CPU which will send the results of data to a voter or a checker and the safety switch off circuitry. We have another problem in that is feeding the GPU subsystems with real-world, real-time input data has to be coordinated so that they start processing at reasonably synchronously. So we have this large amount of infrastructure around the GPU and the CPU, and this makes it impractical to design perfectly synchronous circuits. In an FPGA, there's also complex integrated circuits. We tend to work with system-on-chip architectures which include a CPU and an independent FPGA fabric. The CPU can be used as a feeder CPU for the FPGA fabric, certainly in the boot-up stages and partially in normal operation. However, with a single FPGA, given the fabric is large enough, we can implement two neural networks within that fabric. We can also implement a checker or a voter in that fabric, and so we have the potential to operate much more synchronously than we would if we were applying two separate subsystems. In an FPGA, we also have the potential to directly connect the input and output to the FPGA and the neural networks implemented in that FPGA. So we do not necessarily need a feeder CPU for each data set that needs to be analyzed. With a single entry point to signal conditioning, we also make the acquisition of data substantially easier. We will require a safety switch outside of the FPGA, which checks not only what the voter has agreed on, but also whether the FPGA or the SoC, in this case, is functioning with integrity. So The ramifications for the voter in this case are we need dependability features in the CPU. The voter as an external circuit will need to check the status of each GPU subsystem as well as the generated output, which we believe makes for a somewhat inelegant solution. Certainly complex and complex to certify. We have done some work in networked redundant self-checking units, and we believe that could be also applied here. Again, in an FPGA, the relevant circuitry can be potentially placed into an FPGA. The CPU may not need to be reliable. We do, however, need a checker for the FPGA, and the complexity of this checker has to be researched. If we move on to the experimentation, we take two NVIDIA Jetson boards. The Jetson has a ARM Cortex-A57 paired with a Maxwell GPU, 256 CUDA cores. The ARM will run at 1.7 gigahertz, the GPU at 998 megahertz. We set this up in a headless mode using Linux. We have the application running under a FIFO scheduler, priority 99, and we bind this application to one core. So we try and assume that the application has the highest priority possible for an application running on this operating system. We can use two execution time measurements. We have a profiling function from the Jetson Inference library, and we can use the Chrono library for end-to-end timing, that is job submission and results reception. We use a pre-trained network from the Jetson Inference library, the SSD MobileNet version 2. We load 500 images into a GPU and we execute the inference 100 times for each image, and we measure the execution time. We take a standard data set from the EPFL and use images out of the range of 200 to 799. When we run this on two separate Jetson boards, we see here that the average execution time means out at about 24.3 milliseconds. We see, however, that the profile, the execution time profile, is different for both boards. We also see that we have outliers between 25.8 and 26 milliseconds. And this is, we see as being the maximum time required to perform inferences. We have not yet explained the difference between these platforms and these outliers, which we have to take into account when we're voting on the output of the two subsystems. They need to be explained and preferably also contained. If we try changing the clocking system, that is, we can change the operation clock of the GPU, we can see that the outlier affects systems where the CPU clock is greater than 300 milliseconds. We also see a great variation in the duration or the time of the outliers. If we look at the FPGA setup, we use an AVNet U96 board that has an MP-SoC from Xilinx with a quad-core ARM Cortex-A53 and a programmable logic fabric. We use the DPU, that is the deep learning processor unit from Xilinx. This runs at 210 megahertz. On the AVNet U96 board, we can't increase that clock rate because the power supply of the U96 board will not sustain a higher clock of the deep learning processor. We have clocked the ARM at 1.2 gigahertz. Again, we set up the system, the Linux system, in a headless mode. It's a standard off-the-shelf implementation made available by Xilinx. We have the application running under the FIFO scheduler, priority 99, and the application is bound to one core, just as we did for the GPU application. We have only one execution time measurement. We use the Chrono library here again for end-to-end timing. And we use the same pre-trained network from the Vitis AI library, that is an SSD mobile net version 2, 500 images, each executed 100 times, and use the same dataset from the EPFL. Here we see that we average an inference time of around 43 milliseconds. It is longer than that from the GPU platform, but then it is clocked substantially lower. We also here have outliers round about to 58 milliseconds that require some explanation. Also here, manipulating the clock, we can see quite clearly how the performance increases or improves with an increasing DPU clock. We also see that the outliers can be substantially higher for lower DPU clock rates. So, if we conclude with these, we have two architectures that are substantially different. The GPU architecture requires isolated infrastructure requirements to be operated in a redundant fashion, whereas in the FPGA we can achieve isolation on chip. There is an isolation design flow for FPGAs. And we see that the synchronization of the neural network's outputs and then the later voting are also architecture dependent. In both naive implementations, we see outliers that require explanation and certainly affect the cycle timing of, in this case, classification. The voter will need to have output data valid from both systems before it can actually vote. And these outliers reduce the latency of results. However, the latencies as such are attractive in both implementations. We see that the FPGA platform performs better, or well, at least at a lower power cost, and is potentially cheaper as a dependable version. We also see that the FPGA platform is easier to synchronize to neural networks, and it includes a safety workflow, which helps and reduces costs of a potential safety certification. Future work, two areas. First of all, the voter. We have to see how do we implement a voter for dependability, flaw detection in both the neural network and in the operation of the components. And we're looking at 1 out of 2 voters and m out of n voters. In terms of engineering, we need to explain these outliers. We also need to explain why the mean of classification time from the two GPU platforms is different. We need to look at the dependable circuits. So we have shown that there's potential for an FPGA platform. We need to conceive a solution for that. And we ought to examine network dependability for GPU solutions as well. There are also redundant architectures available from ARM. For instance, the Mali 78AE, which, however, as we see them today, will exhibit many of the issues that we need to solve also for discrete systems. So, I've come to the end of my presentation. I would like to thank you very much for listening to me, and I will be available for any questions in the Q&A session. Thank you and goodbye.